Hi, my name is Caitlin Berrigan, and this is my physics project on generating a computer model of the largest swing in the world, which is in Utah. The first part of this project was finding a rope to use as my model. My rope's dimensions were 30.48 meters in length, 79.83 kilograms was the mass I assumed for the person. 0.0268 meters is the stretch of the rope when it was stretched, and 0.01 meters is the diameter of this rope, and this is a gold line rope, which is general and used for climbing. These are the original values I had for my spring and my mass for my person. For the first question of finding the velocity, I chose, this is my diagram, and I have my Y here, and this is the length of my rope, and this is the pattern of the swing of the person, and this is point A and B. I chose to set it up as an energy system. So for part A, I have E is equal to kinetic energy plus potential energy, but the kinetic energy goes to 0, so you're left with potential energy, and you can exchange the L for the H. For part B, it's you use the same kinetic plus potential energy, but this time the potential energy goes to 0, so you're left with the kinetic energy. Then via the conservation of energy, you can set them equal to each other, the masses cancel out, and you're left with the equation square root of 2GL. Then you plug in your numbers, and I ended up getting 24.44 meters per second. Alright, for the second question, you're finding force of tension. I drew another free body diagram, force of tension going straight up and force of gravity going down. Because this is a circular motion, you're going to use this centripetal acceleration, mv squared over r, and you can substitute L in for r. The reason you're using centripetal acceleration is because the net acceleration in the vertical direction is 0. I said force of tension minus force of gravity is equal to the centripetal acceleration. Then you just continue to solve it out. In the end, you get your L's to cancel out, and you're left with 3mg as your force of tension equation. When you plug in the values as I've shown above, you end up getting 2,347.02 newtons. This is the third question when you're trying to find the tension and the velocity of the speed of the jumper at a 30-degree angle. I made another diagram like I did in the first one, and this time to solve for the height, which is the 30 degrees, and it's the difference here between the swing of the person and the ground, I made an equilateral triangle. So if height 1 is equal to the L sine theta, I use the energy equation, kinetic energy plus mg L sine theta, sine 30 is equal to, you plug in the equations, and when you cancel out the values that you can, you get mgl. And when you plug this into velocity, you have the square root of GL is equal to 9.8 times the length of the rope, and you end up getting 17.28 meters per second. For the second part of the question, I drew another free body diagram, which this is force of tension going off at a 30 degrees angle, and force of gravity is still going down, and because you're once again doing a centripetal motion, you're going to have mv squared over r as your acceleration. I did force of gravity tension is equal to the mg cosine of 30, and I solved it out again, and you can cancel out the L's, and you are left with the equation force of tension is equal to mg plus mg cosine 30. You plug in the values from above, and you end up getting 1,459.86 newtons as your force of tension. For part 4, you're supposed to find the stretch. You need to know force of tension is the same as force of spring. Force of spring is equal to the negative k times the stretch. To find k, you have to know Young's modulus, the area of the rope, and the length. The area of the rope I can find because I have the diameter, and then the length I already have that. To find Young's modulus, which is the elasticity of a rope and is crucial to this equation, you do the force of tension divided by the area of the rope, and then you do the change of and length of the rope over L. So I used all the values from above, and I ended up getting this number. When I plugged it into my K equation, I got E 7,530.23 Newton meters as my K value. I went back into this equation up here. I had set my force of tension from part 2, because this is not at a 30-degree angle. 3mg is equal to negative K delta S. And I solved through this equation, I got 0.0268 meters, and this is accurate because when taking my measurements for an ideal spring or rope, I got 0.0268 meters as my stretch. So theoretically, and then doing it actually, I got the same answer. This analytical process is finding, once again, the stretch in my rope, but at a 30-degree angle. So I used my equation from part 3 at the 30 degrees, mg plus mg cosine 30 is equal to my force of the spring. I once again plugged in my numbers, and I got 0.01668 meters as my change in the stretch. Now, for the biggest part of the Python model I found was you needed to find a new initial position of the person. So for this, I drew a right triangle from the origin following the length of the rope. So I knew that the rope's radius here was 30.48 meters long. And so I did basic trigonometry, and I was able to solve for x and for y, and I got 28.64 and then 10.42. Code for my project is very similar in the structure of Lab 7. In fact, I basically used Lab 7's shell. The only things I changed were these values here. I changed my p-scale, but most importantly, I adjusted my initial value of where the ball or the person is to my degrees that I solved, and the rest of it is all very similar. I found the momentum, I updated the position, I calculated the forces, and I had them print. So then this is the actual demo. You can see the spring moving as it traces the line that it makes, and you can see that it's at a 20-degree angle, which is perfect with what I had predicted. And my FNet perpendicular and my parallel, they all are very accurate for what I should be getting. I have 541 and 685 as my values. The greatest velocity to be when the jumper was at the bottom of the swing, along with this is when the greatest tension on this rope was at the bottom. And that is my project. Thank you for watching.